Hello, my name is Indi Ahmad Affandi, student ID 131182116, and now I will present my final project for MS3200, which is forced convection by internal flow inside a circular duct, with Panji Prayusida as my advisor. Okay, so this is the introduction to the experiment. So it is made in similar to the KV module, but here instead of use of fat plate and fin, we'll use a circular duct to see the effects of varying speed and heat settings of the blower on the airflow, in which it will affect the Reynolds number and Nusselt number. The output of the experiment is to find the heat transfer rate. Okay, so suppose there is an incompressible flow coming through a tube with uniform cross-sectional area, and here in the inlet of the tube there is a mean velocity, and such there will be the mass flow rate through the tube, and the hydrodynamic and thermal boundary layers will develop throughout the tube here, and the relative profile will not change when it reaches a certain point, and the flow will be said as fully developed condition. In here, this point is called the hydrodynamic and thermal entry length, XFD H and T. In our experiment, the flow will be turbulent and a PVC pipe will be used, which is smooth, and hence the friction factor will come into play. By seeing this graph here, we can see that as the flow reaches the fully developed region, the Nusselt number will stay the same, and hence the convection coefficient will be the same throughout the fully developed region. And since the flow is turbulent, the entry lengths are short, which can be approximated by x over d equals to 10. Same for hydrodynamic and thermal. And also, it's reasonable to assume that the average Nusselt number for the entire tube is equal to the value associated with the fully developed region. Okay, so here are some important components and notes for the experiment. So we use our current fluid of air that is provided by the blower to produce turbulent flow, and then we use anemometer to measure the velocity and the temperature of the air in the inlet and outlet of the duct, and also a thermocouple to measure the surface temperature of the duct. And we also assume uniform surface temperature, steady and incompressible flow in a tube of uniform cross-sectional area. The blower here will provide the flow of air that will be given into the PVC pipe, and this blower has two settings for the velocity and the heat that is given, and hence there will be 4 sets of data in our analysis. We use a fan anemometer that will give the velocity and temperature of the flow at a certain point, and in this instance we will use it to measure the mean inlet and outlet temperatures and also the mean velocity in the inlet. For the PVC pipe, it has a diameter of 1 inch and length of 1 meters, and since it is a smooth pipe, it has a roughness of around 0.000003 meters. And to measure the surface temperature, we use the LISA K-type thermocouple with a digital display, and the thermocouple is a sensor that measures temperature and consists of 2 different types of metals that are joined together at one end, and when the joint of these 2 metals are heated or cooled, a voltage is created that can be correlated back to the temperature. And for this thermocouple, the display is read in degrees Celsius, and for the power, it can be supplied by a 12-volt battery or adapter, and for the experiment I opted to use an adapter. Okay, so this is the schematics for the experiment, and as seen here, I placed the blower in front of the pipe inlet, and the thermocouple is placed inside the pipe, and the anemometer will be used to take the readings after the flow is steady. Okay, and these are the methodology for the experiment. First, we prepare the components used as in the schematics, and we turn on the blower and wait for the flow to be steady as it passes into the duct. And then we use the anemometer to measure the velocity in the inlet of the duct and to get the mean velocity, and also measure the inlet and outlet mean temperatures. And then we use the thermocouple to find the surface temperature, and then we find the properties of the air using the mean temperature that we get. Then after that, we need to find the Reynolds number to find if the flow is laminar or turbulent, or in this case, in our experiment, it will be turbulent. And then we find the heat transfer coefficient using the convection correlation for smooth tubes. And then after that, we get the heat transfer rate, and then we do the experiment again for varying fluid velocity and heat settings. Okay, to do the experiment, firstly we take our thermocouple in here, which will read the surface temperature, and we put it inside the PVC pipe. Okay, more or less so. And now after that, we will turn on our blower, which will be pushing the air inside the PVC pipe. Yeah. And now we wait for the flow to be uniform and steady state, so that we can take an accurate reading of the inlet mean temperature, the inlet mean velocity, and also the outlet mean temperature. So after steady state, we take the measurement of the inlet velocity and also the inlet mean temperature there, and also the exit temperature. And now we also take the temperature of the mean outlet, and we take here. Sorry, it's not clear enough. And so this is how I take the data for this experiment. Okay, so that was the video explaining how I directly used the methodology explained as before in the experiment. For the data and analysis and the results of my experiment, this is what I get. And these are all the equations used in the analysis, and of course the data taken is used with varying mean velocity and degree of heat given by the blower. So here, the first experiment, the first setting, so it's a 9.9 meter per second, and H1 means the heat setting is with the same velocity but with different heat setting, H2, and so forth, 15.1 and H2, H1. Okay, and from my experiment, I can conclude that by increasing the mean velocity or the heat setting given by the blower, the heat transfer rate will increase. So if we see here, if we compare experiment 1 with experiment 2, 11 watt and 34 watt, and if we compare experiment 3 and 4, 22 watt and 61 watt, and if we compare experiment 1 and 3 with increasing heat, the velocity, 11 and 22, and also if we compare experiment 2 with 4, 34 watt and 61 watt. Secondly, if I increase the heat setting with constant mean velocity, the Reynolds number and Nusselt number will decrease. So if we compare experiment 1 and 2 here, the Reynolds number is 15,000 and 41. It will decrease to 13,000 and 38. And if you compare experiment 3 with 4, from 21,000 to 55, it will decrease to around 20,000 and 52.7. And finally, if I increase the mean velocity with constant heat setting, the Reynolds number and Nusselt number will increase. So if I compare experiment 1 and 3, here 15,041, it will increase to 21,055.5. And if I compare experiment 2 with 4, with experiment 4 here, Reynolds number 13,038, it will increase to 20,052. For the closing remarks, I suggest using better instruments, since the instruments used are not quite accurate, and also with the placements of the measurements taken, it adds to the inaccurate readings. And also, to determine the steady state, the readings for the temperature and the velocity still tend to offset a little. And finally, I suggest a better place for taking the environment than the one I have done, since I had limited space to use in my house, and also there may be many environmental effects taking place throughout the experiment. That is all from me. Thank you for watching this video.